Most of the world's 1,500 active volcanoes are benign and beautiful sleeping giants for most of the time. But the awesome power of volcanic eruptions threatens death and destruction to more than 1 billion people around the world. Naked Science travels to the ends of the Earth as we ask, will scientists ever accurately predict volcanic eruptions?
We know it'll happen again in the future, it's just a question of when.
It's vital our volcano detective scientists get it right, because somewhere in the world, right now, a volcano is erupting. Volcanoes eject fiery fountains of 2,000-degree red-hot lava, clouds of poisonous gas, and millions of tons of suffocating ash. They kill an average of 850 people per year and injure many more. Nothing can stop an eruption. The only way of saving your life is evacuating the area or heading indoors as fast as you can. But for that, you need to know when a volcano is about to explode. Scientists try to detect when a volcano is going to blow, but they don't always get it right.
Predicting whether an eruption is going to happen is almost impossible.
The science is getting better, because almost every active volcano emits some sort of warning signs. On different volcanoes around the world, scientists seek vital clues that might warn them whether or not an eruption is imminent. Every clue is just part of an elaborate jigsaw, fitting together to give scientists their best chance of solving the prediction puzzle. Scientists study how volcanoes change shape, how hot they get, how electromagnetic waves pass through the rocks, the passage of seismic vibrations underground, and how much gas a volcano emits. But their very first step in predicting what a volcano will do is understanding how a volcano works. And that is a complicated business.
Many people have a fairly simplistic idea of volcanoes. They imagine that there's a single magma chamber, a single vent, a cylindrical vent, and a single crater. Most volcanoes are much more complex than that.
The reality is that under most volcanoes lies a complex network of fractures. Pressure from the vast weight overhead forces molten rock known as magma to the surface. And to make the mysteries of volcano prediction even more difficult, magma is never the same under any two volcanoes. In Hawaii, for example, the magma is relatively thin and runny, releasing dissolved gases quickly and easily, and flowing gently out onto the surface in spreading lava flows. This means that Hawaiian eruptions are rarely sudden, violent, or explosive. Mount Kilauea has been erupting here virtually continuously for years, ejecting as much as 650,000 cubic yards of lava every day. That's enough to fill 200 Olympic-sized swimming pools. Warning signs start in advance of an eruption, and this slow and steady buildup makes them easy to predict. But the opposite is true on some Italian volcanoes. Thick and sticky magma holds vast bubbles of gas, which expand as they near the surface. This gas expansion is so rapid that it powers massive and sudden explosions, ejecting rock and lava in all directions. This thick lava can burst upward with little warning from deep underground in a volcano that may have appeared dormant for years. That makes predicting these volcanoes a far tougher task than it is on Hawaii. This is Italy's Mount Vesuvius, an example of how difficult it can be to predict an eruption. It may look peaceful, but its explosive gas-filled lava makes Vesuvius probably the world's most dangerous volcano. It towers more than 4,000 feet over the ancient and crowded Mediterranean city of Naples. So many potential volcano victims live on and around these crowded slopes that this volcano threatens to injure and kill many thousands. Because Vesuvius has a long track record of natural and human disasters. In 79 AD, Vesuvius blasts an estimated cubic mile of rock up to 20 miles into the air and sends 1,500-degree gas flows rolling at as much as 300 miles an hour into the Roman cities of Pompeii and Herculaneum. 3,360 people die. Since then, there have been around 200 major eruptions.
Raw nature erupts. Cameras record the spectacle of Mount Vesuvius as torrents of molten lava pour down the slope.
The last relatively minor eruption in 1944 kills 47 people and devastates 2 towns on the slopes of Vesuvius. Since the 1944 eruption, the mountain has been quiet, but scientists know that a vast explosive eruption could occur at any time. Such an eruption could even threaten Naples itself, where the volcano overshadows the lives of everyone in the city. Because of that threat, the citizens of Naples put their trust in one of the most ancient, though admittedly the least scientific methods of predicting a volcanic eruption. Twice a year, the religious faithful flock to the Duomo to await a miracle. There, the Archbishop brings forth a glass vial, filled, it is said, with the dried blood of Saint Gennaro. The priest holds high the holy relic in front of the hushed and expectant crowd. He turns it slowly through his hands. Each year, the dried blood of the saint turns once more to liquid. Skeptics dismiss it as little more than a magic trick. Believers take it as a predictive sign that the city is safe from the volcano for at least another year. It's easy to see why people here seize on any clue as to what the volcano may do. Because although at the moment Vesuvius is quiet, when it erupts, the devastation could be total. A recent European study warns that even a modest eruption would mean 500,000 people must evacuate nearby neighborhoods. But is the population ready to leave?
Some people are quite complacent, some people are just not interested.
Volcanologist Carmen Solana studies how volcanoes affect local populations. She worries that those living here have no idea how violent a volcano can be.
Many people don't understand volcanoes. Very many things are going to be occurring that they don't expect. They're going to see lava flows. The ground might be shaking or might be swelling, or they might have been seeing fumaroles and gases coming through the streets. So no, I don't think people know they're going to be subject to.
The city's chaotic traffic threatens any chance of a speedy evacuation. But the biggest problem of all is that nobody knows when the next eruption might occur.
We are not right now in the position of being able to predict eruption. If an eruption is going to be very large or very small, or is going to occur tomorrow or in a month's time, we cannot really predict exactly what's going to happen.
Despite the difficulties, the volcano detectives around the world are striving to improve their prediction techniques. We span the globe, investigating each of the clues that they study, one at a time. First, how do gas emissions indicate if an eruption is imminent? The answer is that the gas coming out of a volcano comes from the molten rock magma underground, and an increase in gas tells volcanologists such as Marie Edmonds that the magma could be rising to the surface.
Volcanic gases are a bit like little messages from the Earth's interior. They really tell us about the magma, whether it's rising, whether it's on the move, whether it's stagnant, what sort of composition it is.
Gases dissolve when their molecules mix with a liquid's molecules to form a smooth solution. Under huge pressure from the overlaying weight of rock, magma can retain vast amounts of gas in solution. It's a little like a bottle of champagne. Pressure held in by the cork enables the liquid wine to dissolve a lot of gas.
As soon as the cork is removed, the gases begin to come out of solution due to the pressure decrease.
Similarly, as magma nears the surface, there is less weight on top of it, and the lower pressure makes the gas less soluble. It expands and bubbles out of the molten rock. The amount and type of gas varies widely from volcano to volcano. To predict eruptions, scientists are most interested not in what type of gas is present, but whether or not the gas emissions are increasing or decreasing from the norm. Mount Etna in Sicily, for example, pumps out as much as 3,000 tons of sulfur dioxide every day. But Etna's gas emissions increase before an eruption, as happens in 2000 with these spectacular smoke rings. Soaring 3,000 feet into the air and expanding to more than 600 feet across, the rings of gas and steam indicate that the volcano is coming to life. The eruptions that follow send ash 2 miles into the air to fall 15 miles away from the mountain. Edmonds is an expert on the sort of high-tech equipment used on Etna to analyze volcanic gases. Now, she is on Hawaii, evaluating new equipment that can analyze volcanic gases from hundreds of yards away from their source.
It means it's a lot safer. You don't have to get right up close.
The United States Geological Survey warns that volcanic gases are a hazard to human health on most of the world's volcanoes. Pungent sulfur dioxide from Hawaii's volcanoes can irritate eyes and skin, and in past eruptions, harms crops up to 12 miles away. Carbon dioxide can kill in high doses. Hydrogen chloride forms acid rain. The rarer hydrogen fluoride can damage your heart. Edmonds' $100,000 infrared spectrometer recognizes all of these gases. Its portability and ability to work from a distance means that scientists can safely gather more data than ever before.
The key thing, I think, with studying volcanoes is the technology you use to measure these things, and it's getting better all of the time. We're seeing things with this that we've really never seen before.
Thin and runny magma releasing gases gently and thereby relieving the pressure bit by bit is little threat to anyone. But other volcanoes, such as Soufriere Hills on Montserrat in the Caribbean, Mount St. Helens in Washington State, and Vesuvius in Italy, are highly explosive. Their magma is rich in silicon. It's more viscous and, crucially, holds on far more tightly to the dissolved gases. The gas doesn't bubble out until the magma is closer to the surface, and when that happens, it happens with a bang.
This is often the scenario whereby you get an explosion, a volcanic explosion.
The lava and debris ejected from volcanoes forms more than 80% of the surface of our entire planet. There are some 1,500 active volcanoes around the world. Their awesome power has always attracted cinematographers seeking spectacular pictures. Cameraman David Lee is on the Caribbean island of Montserrat in 1995. He knows the volcano is threatening to erupt, but he pushes his luck to the limit by climbing alone to a high mountain ridge.
It's right in here you start to hear it. and it makes your heart beat real fast. And it's hot already, and it's spewing right now. And I'm getting out of here. I'm just going to take a snapshot.
The volcano explodes into life.
Now do I look scared? I'm not out of here yet. I'm only down about 600 feet. If the whole thing went, wouldn't have a chance up here. I think that's the closest I ever thought about being dead.
Lee survives, but over the next few years, millions of tons of volcanic ash bury parts of Montserrat, perhaps forever. In the face of such overwhelming power, scientists constantly seek ways to gather vitally important data without putting human life at risk. Perhaps robots can collect data where humans, quite sensibly, fear to tread. Volcanologists in Sicily set out to design a robot that could go where no scientist had been before and come back safely. Enter RoboVolc. Scientists are confident that RoboVolc can cope with just about any terrain the mountain may throw at it. Its sensors are resistant to the intense heat of a volcanic environment. It records temperatures, measures the angle of slopes, and even collects rock samples with a remote-controlled arm. Machines such as RoboVolc that relay information back directly from the field are reducing the risk for all those who study volcanoes. But there are some eruptions so awesomely powerful that anyone within miles of the volcano is in deadly danger. Seeking clues that could help predict the next terrifying eruption, we revisit the disaster of Mount St. Helens in Washington State. It's 1980. Scientists fear that the volcano is going to blow, not only because of its changing gas emissions, but more importantly, because the ground is changing shape. And as every volcanologist knows, only vast underground volcanic pressures can move a mountain. Before an eruption, molten rock forces upward under almost unimaginable pressure to fill the underground magma chambers. Cracks may open up, land may subside, or the Earth's surface may actually rise up in a clearly visible bulge. It can change the very shape of the volcano. And this ground deformation gives volcanologists another important clue in their quest to predict a coming eruption. Ground deformation becomes the most important clue of all on the Mount St. Helens volcano in the spring of 1980. It's caused by the intrusion of magma underground and gives scientists a vital warning about the ever-growing danger of an eruption. Volcanologist Don Swanson is there as the volcano starts to stir in the spring of 1980.
It was an exciting time for me and for all of the others there, but I don't think we ever anticipated or came close to anticipating the magnitude of what was going to happen.
The north flank of the volcano develops an unsightly half-mile-wide bulge, a deformation process for which Swanson has a very human analogy.
Kind of like a stomach rumbling. You sometimes have a great swelling, and of course we all know about gas coming out of the stomach. So I think there are these very earthy metaphors that you can use, but you're listening for a volcano's burp.
Despite all the warning signs, nobody can say for certain if and when the volcano might erupt. Soon the bulge in the mountainside is growing at an incredible rate, as much as 5 feet in a single day, as molten rock moves up inside the volcano. Cracks open up in the surrounding slopes as the bulge pushes more than 450 feet outward from the mountainside. Scientists from the United States Geological Survey monitor the movements with electronic tilt meters, which radio their measurements to the scientists' laboratory. These are signs that the scientists cannot afford to ignore. The area is evacuated. On the morning of May 17th, Don Swanson is the last person to fly to the very top of the mountain. He asks his helicopter pilot to land for a closer look at the way the volcano is changing.
We walked over and took a look into the crater that had formed at the summit of the volcano, and we had no idea that the next morning the volcano was going to fall apart.
8:32 a.m., May 18th, 1980. A massive landslide rips the mountain apart as 23 square miles of rock slide down the north flank of Mount St. Helens. The landslide releases the weight pressure on the magma beneath, popping the cork from the champagne bottle and causing the most destructive eruption in the history of the United States. It pumps about 520 million tons of ash up to 12 miles in the air and turns day into night for people as far as 250 miles away. Pile that much ash up on a football field and it will reach up to 150 miles into the sky. That morning, Don Swanson is once again in a helicopter with a bird's-eye view of the terrifying natural wonder unfolding below.
Flying around the volcano is really an awesome experience. Looking out, we can see that this is an exceptionally energetic eruption column, and all of us are overwhelmed by what we see.
Gene Hutchinson is also overwhelmed that day by the sights and sounds of Mount St. Helens erupting. He revisits the national park surrounding the volcano.
We could see this huge plume going up, I'm told, 65,000, 70,000 feet in the air. There was actually people that were burned to death due to this high temperature.
Once the mountain erupts, a huge volcanic flood, known as a lahar, rushes down this valley. All the timber in the area is blown down for miles around. Within 2 weeks, some of the ash drifts around the globe. 57 people die in the eruption that causes more than $1 billion in damages. And yet, in terms of the accuracy of scientific prediction, the Mount St. Helens disaster is considered a relative success. Scientists using ground deformation as a major clue give enough warnings for thousands of people to safely evacuate the area. The measurement of ground deformation remains a valuable prediction tool today, especially at our next port of call in Hawaii, home to some of the world's most active volcanoes. In Hawaii, geophysicist Mike Poland uses a network of ground positioning satellite reflectors to measure deformation on the Mauna Loa and Kilauea volcanoes.
We can get an idea of whether or not there's magma that may be accumulating in a chamber or reservoir below the ground.
His equipment triangulates with space satellites, just like your in-car satellite navigation system, accurately fixing the position of each GPS station around the volcano rim to within a fraction of an inch.
If there were magma that were starting to accumulate in some kind of subsurface chamber, then we would expect the stations on the opposite side of the caldera to be moving further away as the volcano inflates like a giant balloon.
Poland's data shows that Kilauea inflates and deflates like a balloon in a regular cycle as magma pushes into underground chambers and then empties out in one of the regular eruptions. On Kilauea, as on many other active volcanoes, the volcano detectives also study the third of our eruption indicators: temperature changes. They record how hot it is on and around the volcano. Here on Hawaii's slow-moving lava flows, scientists get close enough to push a thermocouple temperature recorder directly into the liquid rock beneath. This lava reaches temperatures of around 2,000 degrees, about 4 times as hot as a typical pizza oven. Scientists have to withstand incredible temperatures for long enough for the probe to take a correct reading, and that is not always possible. Volcanologists joke that the accuracy of a temperature reading is inversely proportional to the comfort of the scientist making the measurement. Despite the difficulties, temperature measurements can provide vital information about the likelihood of an eruption. The theory is that hot magma rises toward the surface in the buildup to an eruption and makes the volcano hotter. Therefore, the hotter it gets, the more likely it is that there will be an eruption. Similarly, if temperatures drop, then the risk of an eruption is reduced. The temperature even gives clues to the lava's chemical makeup. Magnesium-rich lavas, for example, tend to be hotter. And that can reveal which magma chamber it comes from and its possible route to the surface. But to save our lives, scientists need to predict not only when a volcano might erupt, but also what death and devastation an eruption will cause. Lava flows kill people and destroy homes. The temperature of the lava helps scientists establish how far and in which direction it will go. Because it's generally true that the hotter the lava, the further and faster it will flow. Volcano detective Harry Pinkerton is one of a team recording lava temperatures to try and divine how far lava will flow down Mount Etna in Italy. Lava flows on this mountainside regularly terrorize local villagers.
Eruptions have been pretty devastating for people who live in this area. They've cut off the roads, they've cut off the communications, and a large number of vineyards and tourist complex and houses have been destroyed.
Mount Etna is Europe's largest and one of its most active volcanoes, regularly blasting lava bombs, gas, and ash from the 4 craters near its peak. The slopes of this mountain reveal clear evidence of just how hot the lava is when it pours out of the volcano. Pinkerton is walking over lava that solidified 5 years ago, yet there is still enough heat in these rocks to turn moisture into steam. During eruptions, the team sets up a thermal imaging camera directly in the path of advancing red-hot lava flows. The camera is similar to an ordinary video camera, but this one gathers evidence of heat emissions rather than reflected light to create a moving image. White is hot, black is cool, with a range of colors in between. The technology to take moving heat pictures of this quality has only been developed within the past few years. In ordinary daylight, the lava flows appear predominantly black and gray, with glowing red areas where moving rocks reveal the underlying heat. But look at it through the thermal camera, and the picture changes dramatically. This is a daytime picture of an Etna lava flow captured on the team's thermal imaging camera. You get some idea of the scale by looking at the thermal image of one of the scientists highlighted at the bottom of this picture, working just a few yards in front of the flow. That scientist was Pinkerton's colleague, university researcher Matt Ball.
Well, to be stood next to an active lava flow is quite an amazing experience, not only from a scientific, but also for me from a personal perspective.
Ball's analysis of the thermal images reveal that lava flows can reach almost 2,000 degrees Fahrenheit.
You get to notice the raw power that a volcano has and how insignificant you are in comparison to that power.
To collect accurate data, the scientists get dangerously close to an active vent, 6,000 feet up the side of the volcano. The temperature of the lava drops 100 degrees or more within a single second of being exposed to the air. a cooler crust forms quickly, distorting the temperature readings. So Pinkerton dons a protective suit and dips a rod into the dangerously hot lava, exposing the extreme heat of the subsurface flow to the camera's gaze. Hot lava from vents like these runs down a volcano's slopes in depressions and valleys, forming spectacular rivers of fire. But the path of the lava is complicated because it cools rapidly at the edges, slows down, and solidifies on the top. This process gradually creates an insulated roofed-over tube that keeps the underground lava river hot. The hidden lava flows faster and further in the tube than it would do in the open, breaking out sometimes great distances from the original vent. The most spectacular lava tubes form on Hawaii. Here, they pour lava at temperatures in excess of 2,000 degrees directly into cool seawater, with astonishing results. On Hawaii or on Etna, the creation of lava tubes makes it hard to predict the path of the molten rock flows.
This unpredictability is something that I think people who are living in volcanoes have to accept and have to live with.
But the way that lava flows is not the only unpredictable event accompanying volcanic eruptions. Magma, forcing its way to the surface, follows a random path through fractures and weaknesses in the underlying rocks. And the energy waves it creates can help predict when a volcano will erupt. Magma and gas rising inside a volcano crack open and force apart solid rock. The shifting and breaking rocks create seismic vibrations, waves of energy, that scientists on the surface can pick up from miles underground. Studying those energy waves, the science of seismology, gives scientists their fourth set of volcanic prediction clues. To see the very latest techniques in the use of seismology to predict volcanic eruptions, we travel almost halfway around the world, from Italy's Mount Etna to New Zealand. This is Mount Ruapeu, 9,000 feet high, and one of the country's most active and explosive volcanoes. Ruapeu is a native Maori name meaning pit of noise. An eruption here in 1995 threatens the life of New Zealand cameraman Jeff Mackley.
The crater suddenly erupted only a matter of a few yards in front of me.
Get ready to run, guys.
An airlift saves Mackley's life and gives him his first lesson in how difficult it is to predict an eruption, a lesson he's taken to heart.
They are the most dangerous thing on the planet. You get in, you get a few pictures, and you get the hell out of it.
Underground magma movements before an eruption send scores of seismic tremors, mini earthquakes, rippling through the ground. So ever since surviving the Ruapeu eruption, Mackley carries his own portable volcanic prediction kit in his backpack.
I'll place a half-full bottle of water on the ground and use that as a makeshift seismograph.
Whenever he's filming on a volcano, Mackley watches out for earth tremor vibrations on the surface of the water to warn if an eruption is imminent. Mackley is a video photographer rather than a scientist, but scientists too are studying seismic tremors on Mount Ruapeu, but with somewhat more professional equipment. Martha Savage of the Victoria University of Wellington in New Zealand studies how earthquake-generated seismic waves travel under a volcano. She buries sensitive seismometers on the slopes around the volcano to detect the slightest seismic waves from subterranean earthquakes. Then she tests that they are working in the simplest way possible, by creating a few seismic vibrations of her own. Data that Savage and her team collect from Ruapeu could be the key to a new and more accurate method of predicting volcanic eruptions.
I was just really excited when it turned out we have this technique that maybe we can really see changes on volcanoes, and maybe we can use this new technique to help predict volcanic eruptions and save people's lives.
Earthquakes create vibrations radiating out from their point of origin, what scientists term S-waves. They shake the rock particles from side to side as they travel outward.
It's kind of like a Mexican wave. The actual motion of people's hands is up and down, but the motion of the wave is perpendicular to the direction that the wave itself is traveling.
Savage knows that S-waves can split within rocks, with one component at right angles to the other. One part runs rapidly, aligned with rock fractures. The other slows down as it runs across the direction of the cracks.
If you were running through a field, say, and the field had a lot of streams running down it, you could run much faster if you could run parallel to the streams than if you had to run across the streams.
Determining the direction in which the waves run faster shows Savage the alignment of most of the rock fractures below the volcano. Her new discoveries on Mount Ruapehu reveal that those fractures alter their alignment by as much as 90 degrees in between eruptions.
So we saw this big change, and we were surprised because we hadn't expected to see a change.
Savage theorizes that rising pressure before an eruption squeezes shut cracks running parallel to the magma chamber and opens up new cracks at right angles. She believes that using S-wave speeds to detect shifts in fracture direction around other volcanoes could help predict eruptions. Savage's work does offer real hope for the future, but still cannot offer the one thing that every volcanologist most desires: the ability to actually see what is happening under the Earth's surface. We just cannot dig down deep enough to ever discover for ourselves exactly what is happening 100 miles under a volcano. So, as Etna expert Harry Pinkerton knows, the only certainty is that volcano structures are far more complex than you may think.
Etna, for example, has 4 summit craters, and the magma is stored in several different reservoirs. At least that's what we think is happening. One of the critical things that we need to do is to identify where the magma is, and that then gives us an indication as to how rapidly it's going to ascend to the surface.
Now, new computer-aided models are picturing the shape and size of magma reservoirs under a volcano. Dr. Max Maydew from the University of Lancaster in England is using cutting-edge electromagnetic techniques to produce pictures from 80 miles and more below the surface of our planet. Maydew produces pictures of the rock structures below volcanoes, like this one from 18 miles below the Tingcheng volcano in China. The scarlet central bubble is thought to be a magma chamber, the dark blues solid rock, and the light blue, fractured rock.
I'm excited that we are able to map structures deep down in the ground.
Maydew became a volcanologist because his dream from childhood was to see what happens under the ground.
Hopefully, maybe in the near future, one should be able to predict volcanic eruptions using this type of method.
The power to see such structures deep underground comes from an unlikely source above our heads, because what helps to create these pictures is lightning. Lightning strikes create massive waves of electromagnetic energy, waves which travel around the world, bouncing off the ionosphere 40 miles above us. Their energy can penetrate deep into the ground, reflecting off rocks up to 3 miles or more below the surface. These currents meet different degrees of resistance as they meet different types of rock. To reveal the underlying rock structure, Maydew lays out electromagnetic sensors over hundreds of feet on the surface of the ground. He aligns them carefully along the 4 points of the compass so that he can factor in the influence of the Earth's own north-south magnetic field. Data from the sensors feeds directly into a computer out on location. Meiju uses the power of lightning to see lava chambers a few miles below a volcano. But the early signs of some volcanic eruptions can be found far deeper than that, in chambers up to 100 miles underground. To look that deep and improve volcanic prediction techniques even further, Meiju needs an even stronger power source for his electromagnetic waves. He uses the power of the sun. Solar flares regularly pump out energy waves of almost unimaginable power. The Earth's magnetic field deflects much of this energy toward the poles. That's what creates auroras. But the impact of solar flare particles sends ultra-high energy, long wavelength electromagnetic waves rippling through the Earth. They search far deeper than the relatively puny lightning strikes. Measuring rock resistivity to these sun-induced waves produces pictures like these from under 2 volcanic islands in the South China Sea. For the first time, this innovative technique shows how magma may race to the surface. This is the volcanologist's dream come true. Everyone living near volcanoes badly needs that dream to come true. All the scientists' calculations cannot cope with the unpredictability of nature. We do not know when the next devastating eruption will occur. And many volcanologists are still haunted by the memory of failures of volcanic prediction. Tragic failures that cost the lives of more than 20,000 people in one gigantic eruption. 1976. The Caribbean island of Guadeloupe hears a terrifying warning. Volcanologists say that the island's massive La Soufrière volcano may soon erupt. They report that gas pressure is building up. The authorities heed the scientists' grim warning. 72,000 people are evacuated at a cost of millions of dollars. For 4 months, the capital city of Basse-Terre is left as a ghost town. As the scientists continue to monitor the volcano that looms over the area, houses are abandoned and desperate farm animals roam the streets looking for food. But the scientists have got it wrong. La Soufrière never did violently erupt. Less than a decade later, that failed prediction comes back to haunt volcanologists when smoke starts rising from the 17,000-foot snow-covered summit of Nevado del Ruiz in Colombia. Scientists warn that a likely eruption will send volcanic floods of melted snow and ice toward nearby towns. This time, the scientists have got it right. But the authorities do not order a full evacuation. The volcano erupts in November 1985, and the predicted floods bury the entire town of Armero under a sea of gray ash and mud. An estimated 23,000 people die, 4,500 are injured, and 8,000 made homeless. The disaster perfectly illustrates the dilemma facing all volcano scientists. Cry wolf too often, and nobody listens. Fail to issue a strong enough warning, and thousands may die. So how can we better detect what a volcano is going to do?
We're going to have to use a combination of techniques to successfully predict eruptions at volcanoes.
To examine how you can combine all of the evidence from different sources, we travel close to the Arctic Circle, to the island of Iceland. The island has about 130 volcanic mountains, of which 18 have erupted since people first settled here 1,000 years ago. Scientists, such as Matthew Roberts, use computer models that analyze data from all sorts of different prediction techniques to produce one combined prediction. Iceland faces greater danger from its volcanoes because of where those volcanoes are located. Some of its biggest and most active are buried under deep glacial ice. When they erupt, up to 10,000 tons of meltwater is produced every second, turning streams into monster lahars, volcanic floods. In addition to this deadly threat to their own citizens, Icelandic scientists have another responsibility to thousands of air travelers crossing their country. Scores of aircraft every day fly over Iceland's volcanoes on the main transatlantic air routes linking America and Europe. Flying near a major eruption runs the risk of volcanic ash being sucked into jet engines.
Many planes have stalled in volcanic ash plumes, and we have just a matter of minutes to try and move the flights to a different location.
Facing such a volcanic threat, Icelandic scientists are among the world leaders in monitoring the dangers. A network of seismic recorders make up an automated warning system that runs without human intervention. Although the sensors themselves need maintenance in their remote locations on this sparsely populated island. The instruments are some of the most sensitive in the world and can detect even the faintest earth tremors.
With the right equipment and scientific know-how, you really can take the pulse of an active volcano.
Iceland also boasts a network of water sensors placed in the rivers around the island. Changes in water temperature, depth, or in the type of volcanic gases dissolved in the water all give warning signs. And the latest technique used in Iceland for measuring ground movements and deformation is INSAR, Interferometric Synthetic Aperture Radar, a fancy name for a satellite system that closely resembles the radar guns a policeman uses to issue a speeding ticket. A satellite fires a radar beam to Earth to record a volcano's exact position. On a subsequent orbit, the radar beam fires again. Comparing the two images shows up the slightest shift in the land around the volcano. Together, this comprehensive mix of detection devices records the volcano's state of health.
No volcano will erupt without almost screaming a warning to the scientists. It's our challenge to be able to firstly listen to that scream and then be able to understand it.
Rather than relying on any one system of volcano prediction, scientists here constantly refine computer models that collate and analyze information from all of the different prediction methods. Success comes when the volcano Hekla bursts into life and scientists accurately predict the eruption to the day, the hour, and to the very minute.
We know what sort of signatures the volcano will emit before it erupts.
Icelandic scientists believe they are close to the volcanologists' holy grail of producing practical predictions in time to save lives.
It would be a failing on our part. It would be a scientific failing if the volcano erupted without us being able to issue some form of advisory beforehand.
The Icelandic experience combines all of the standard methods of volcanic prediction in one computer-controlled and monitored package. Experience gained here is gradually improving volcano monitoring in other countries such as Italy, where hundreds of thousands of people remain in the potentially deadly shadow of Mount Vesuvius. But despite their best efforts, scientists may never be able to tame the overwhelming power of nature.
No matter how many instruments you deploy on volcanoes, no matter how much time you spend monitoring the volcano, there are always going to be events that take place which are not going to be predicted.